All right, let's do another one here. And again, I have a Maclaurin series. So if I'm talking about Maclaurin, what is my A? Yes, good. Automatic 0, right? Okay, so let's do this one for f of x is equal to 1 over 1 minus x. Oh, have we seen this little beauty before? I think so. This is what we did whenever we manipulated those at the end. And I said, sit tight. We're going to figure those out next section. And here it is. So now we're going to prove what we already know. So we're now going to come up with the proof behind what we were already given at the end of that last section when we manipulated this geometric series. Okay, let's do it right now. We want to write the first 4 non-zero terms. Okay, so set it up. I'm going to put a lot of space in this little middle piece here. Because remember, our purpose with the derivatives, I can't do two things at once. The purpose of this is to come up with that pattern. All right? So we want to come up with a pattern. And so I'm not necessarily going to multiply everything out because the goal is to find a pattern. So I'm going to approach this just a little bit differently. And I know this is Maclaurin, and that's where that 0 comes from. All right. So I start with 0, which is my actual function. With this 1 over x situation, I'm going to write this as 1 minus x to the negative 1 power, because then I can just chain that. There's no need to do a quotient rule on this rational expression because my numerator is a 1. So if I were to plug 0 in here, 1 to any power now is 1. Okay. So now I'm going to bring the negative in front. I have 1 minus x to the negative 2 times the derivative of the inside. When I take it times the derivative of the inside and you chain that, that's where that negative 1 comes in from the inside, and it's going to make that positive. Do you see that? So you chain it. So this blue negative comes from bringing my exponent down. Then I chain it. So I multiply it by a negative 1. So a negative times a negative is a positive. And again, I come up with 1 on this instance. Then I'm going to bring the negative 2 in front. Go back to blue. The negative 2 in front. And I've got 1 minus x to the negative 3 times the derivative of the inside is going to make that positive. So now I end up with a 2 over here. And I'm going to make this blue also. All right. Now I'm going to bring that 2 here times that negative 3. And I have 1 minus x to the negative 4 times the derivative of the inside is going to make that a positive. All right. Oops. I'm going to bring this down. It says the first 4 terms, but we're going to do an extra one. So now this is going to be 2 times 3. So now I have 2 times 3 times this negative 4, 1 minus x to the negative 5 times the derivative of the inside. So now I have 2 times 3 times 4. And you see we're just going to keep seeing that pattern over and over again. So you tell me, what kind of pattern are we seeing over here? Yeah, right? Factorials. So I'm looking at these factorials. This is really 4 factorial. This is 3 factorial. 2 factorial. 1 factorial and 0 factorial, because remember 0 factorial is 1. Okay, so if I'm using my formula, right, can't forget it, nth derivative of a over n factorial x minus a to the n. I'm sure you've rewritten it enough now, it's in there. This is now my nth derivative up here. Is a 1 plus, this is now 1 For my first term, I've got 1 for my second term. 1 over 1 factorial, and then x to the first power. Now this is going to be 2 factorial over 2 factorial x squared. It's Maclaurin, right? So I'm minusing 0, plus 3 factorial over 3 factorial x cubed, 4 factorial over 4 factorial x to the 4th, and then that is infinite, even though we're only doing the first 4 terms. And we actually did a few more here, but do you see that? That's why I keep this written out, is so that it helps us find patterns. And now look what happens. 1's cancel, 2's cancel, 3's cancel, 4's cancel. My actual polynomial here is 1 plus x squared plus x cubed plus x to the 4th, etc. If I wanted to find that pattern of 1 over 1 minus x, my series, from k equals 0 to infinity is going to be x to the k. Good. Because if I were to plug a 0 in, so do it in your head, plug in a 0. Oh, anything to the 0 power is 1. Plug in a 1, x to the first. Plug in a 2, x squared, 3, x cubed, etc., right? Good. Now, I'm charged, so now I have my series, right? But now I have to figure out my interval of convergence. That's what my question asked for. Now, we know from our previous problems what it is, but we have to check it here. If I have this series, what test are we going to do? Yeah, root test. It only makes sense. So I'm going to take my limit as k approaches infinity of x to the k to the 1 over k power. And then this limit is going to be the absolute value of x. In order to make my statement true, right, with my root test, I have to make this less than 1. This is root test criteria, in case you forgot. All right. So I know that this is my radius of convergence for 1, and I know that I'm going from -1 to 1. Then check your endpoints. I'm going to look where x is -1, and I'm going to plug that into my series, where I'm going from 0 to infinity of -1 to the k. When I take this limit of -1 to the k, this diverges, because it's equal to plus or minus 1, which is not equal to 0. So it diverges by the divergence test. All right? And if I'm going at +1, my limit is equal to 1, which does not equal 0. Again, diverges by the divergence test. So my interval of convergence for this problem, -1 to 1, which we already knew. And a lot of times it's written as the absolute value here of x is less than 1. So that's a common way to write that. Does that look familiar? Right? Look at that. So before I said, oh, this is a geometric series, we're going to work this out. So this is your geometric series, and we just proved why what I told you to accept last time was true. All right, let's do another one. Practice, practice, practice. That's what's going to get us good at these. And seeing those patterns, that's where people struggle with these, is seeing the patterns. So I want to keep practicing to make sure that we can find that out. Find the first 4 non-zero terms. Oh, this one's literally just finding the first 4 non-zero terms. Oh, and it's not Maclaurin. We're centered at f of x is equal to the cube root of x centered at 8. Okay, cool, right? So this was a legit Taylor series, not just Maclaurin. Okay. And look here, it is not asking us to find the series. We just are being asked to find the first 4 non-zero terms. So I bet these numbers get wonky. All right, so let's do it though. 0, 1, 2, 3. These are the first 4 non-zero terms. So my first term is x to the 1/3. Whenever I plug an 8 in, we get a 2 out of that deal. Bring that in front. 1/3 x to the negative 2/3. All right, so this will be 1/3 and x to the negative 2/3 here. That's going to be in the denominator, so this will be 1 over the cube root here of 8 squared. I know every time you get this cube root of 8, that's going to be a 2, so then that's where I get this 2 squared. Okay, let's try again. So now I have 1/3. Oh, we just need the first 4 terms. We don't really have to come up with a pattern. Okay. Okay, that works out. So if I don't have to come up with a pattern, but I'm still going to multiply these out because, so I've got 1/3 times a negative 2/3. X, if I subtract 3, is a negative 5/3. Right? So then that's going to actually end up being to the 5th that I have it because I've got this 5th exponent right here. So I've got 1/3, negative 2/3, and 1/2 to the 5th. All right, so 1/3, negative 2/3, negative 5/3, x to the negative 8/3. So 1/3, negative 2/3, negative 5/3, and then I have it to the 8th. And here a negative times a negative is a positive, so I'm going to lose those negative signs right there because I don't need them. Oops. Okay, there's our first 4 terms. Yikes. But we got this. So my first term is always just the first number, so that's good. 2. Then I have 1/2, or pardon me, 1/3 times that 1/4. Times, centered at 8. Times 1 over 1 factorial, and this is x minus 8 to the first power then. Okay? Minus, so I've got 2 ninths times 1/2 to the 5th. Oh man, we can do this. Times 1 over 2 factorial, x minus 8 squared, plus 1/3. So I'm going to put these together. So 10 over 27 is what we're getting there, right? 10 over 27 times a 1/2 to the 8th times 1 over 3 factorial, x minus 8 cubed. Wow, I'm glad we don't have to find a pattern for this, because yike-a-rooski. Okay, so there's not too much going on in that first piece there. So this is 2 plus 1/12 times x minus 8. Here, this 2 cancels out with that 2, so we're good. So I just have 9 times 2 to the 5th is what, 32? So what is 32 times 9? 18, 27, 28, 288? Is that what you guys get? Minus 1 over 288x minus 8 squared plus. Y'all, I'm going to do a calculator right now. If I would have to work this out, I would totally be doing a calculator. This is 3 times 2 times 1. That's 2 to the 8th. So I know one of these 2's right here is going to take out one of those 2's, leaving me with a 5. So my numerator for this one is going to be 5 over 27 times 3 times 2 to the 8th. Get out your calculator. I'm not doing that, we're not doing that. 20,736. Okay, so here's a news flash for you. I'm not going to have you do that. I would be totally fine. I'm not going to give you any big numbers like that where you're going to have to pull that off. If you get something like that in my math lab, get out your calculator and use it, right? We're not going to mess around with this kind of stuff up here. That little tiny multiplication by one term is no big deal. But something big like that, I'm not messing with that. So here we're just looking back through there. And this one does not say it's just the first 4 terms. So it's really just giving us practice here with finding a series other than 0 instead of just a Maclaurin. All right? Woo! But it's not bad. The process is exactly the same. The biggest issue on this one was they had those kind of crazy numbers there.